Alright, grade 12 chemistry. We're talking about Hess's law today. We have a very, very simple learning goal. We're first going to learn what is Hess's law, and then we're just going to do 3 practice problems with it. So I won't take too long to talk about Hess's law. Hess's law is, to me anyway, a fairly logical conclusion. But here's what the curriculum says we have to do. We have to solve problems related to energy changes in a chemical reaction using Hess's law, and state Hess's law and explain its use using examples. And here's a quick descriptor of the logic behind Hess's law. Now, let's say we're climbing a mountain like Mount Kilimanjaro here. We could take the direct path to the summit up like this, or we could take a winding path like this. But at the end of the day, you're at the summit and you've gone there from the base, so your energy change, the visible energy change, is the same. If you saw someone here and then someone up here, hours and hours later, you wouldn't know which path they took, and we're going to use the same kind of logic for chemicals. So that's the basic logic for Hess's law. Here's the actual kind of statement of it. Hess's law, this is Jermaine Hess. He came up with it, I guess. It says that the enthalpy change of a reaction is independent of the steps taken. So the energy change is independent of the steps taken. Just like the guy at the bottom of the mountain and the top of the mountain, you don't know what steps they took, but the energy change is the same. Let's say if 2 people took these 2 different paths and then, I don't know, skied down the mountain or mountain biked down the mountain, they would both gain the same amount of energy coming down, independent of how they got up. So that's the concept behind Hess's law. Here's an example for the formation of NO2. So nitrogen plus oxygen gives you NO2. You can do it in one step. It takes an input of 68 kilojoules per mole. Or you can take your nitrogen and your oxygen and make nitrogen monoxide here. And then take the nitrogen monoxide and add another oxygen. Then you get nitrogen dioxide. And this first step is an input of energy. The second step is a release of energy. If you add these up, 180 minus 112, you get the same 68 kilojoules. Just like the amount of energy here, it's a bunch of small steps versus one big step. The same kind of input. And it makes a certain amount of sense if you think about the bond energies, right? This has a certain amount of bonds at the start and the end, and then this has a certain amount of bonds at the start and the end. It's the same bonds at the start as at the end, so it should be the same energy. Here it is graphically, so some people like to see this graphically instead. Here's the one-step process, N2 plus 2 O2s making 2 NO2s, right? Just one step. I don't know what the activation energy is, but I know that the delta H is 68 kilojoules, plus 68 kilojoules. Here's the two-step process. We have a big jump, right? A big jump, plus 180 kilojoules. There it is, 180 kilojoules. Big jump. Don't know the activation energy, I just know that to get to here with that big jump. Then we have another little bit of activation energy, and then it falls down by 112 kilojoules. But overall, the same increase, plus 68 kilojoules of energy. So yeah, we have the same energy input or release, multiple steps or one step. And this can be helpful for us as thermochemists. Sometimes you can make activation energy smaller by doing a reaction in multiple steps, and then you can do it at smaller temperatures or with different reactants and things like that. So being able to do the same reaction in multiple steps is sometimes an advantage. Other times it isn't. Here, actually, the single step process is probably better because it's just a jump of 68 kilojoules. Here, your first step is to increase by 180, so probably less favorable than this one here, than the one-step process. So that's what Hess's law is. Hess's law is very, very simple. It's just this kind of logic, this kind of basic physics logic applied to chemistry. I don't really know why it's named after some dead white guy, but I guess 1840, that was a revolutionary idea. Alright, having said that, let's get into some practice problems. So that's our next thing, is we're just going to do some practice problems for the rest of this video. Hopefully it won't take too long. So I'm just going to change this down here, practice problems. Now the big thing about Hess's law is that we're allowed to flip a reaction, and we're allowed to multiply reactions by, like in algebra, we multiply the whole thing by one by one coefficient. We also divide things by 2 or by 3. When we do that, we have to do the same thing to its energy terms. If we flip a reaction, the energy term goes from positive to negative, from negative to positive. If we multiply a reaction by 2, twice the energy. If we divide a reaction by 2, half the energy, and so on and so forth. Here's a simple one. There's a really great tutorial about this in your textbook, Nelson Chemistry 11 on page 316, if you have that book handy. If you don't, there's also lots of practice problems in the open text, which you'll see at the description of the video. We're trying to figure out the delta H of turning graphite into diamond. How do you turn graphite into diamond? So, squeezing it and putting in energy, I guess. So, if we want to figure out this reaction, maybe that's difficult. It's hard to turn coal into diamond, but we can burn the graphite and we can burn the diamond in oxygen, right? We can just combine it with oxygen and burn it, and see how much energy comes out. When we burn the graphite, we get 394 kilojoules of energy. When we burn the diamond, we get 396 kilojoules of energy. And then we can use Hess's law to work out from these two what this reaction would give us, because now we have a two-step process we can do. We can burn, we want to go from graphite to diamond. We're going to burn the graphite to CO2, take the CO2 and turn it into diamond. Right? That's the kind of concept that we want to get into. We want to take this, right? We have, if we just draw it real quick, I'm going to, so we have, this is the one for diamond, that's the one for graphite, this is the one for diamond, which will have a slightly bigger drop, right? So I'm going to start it slightly higher, right? Slightly higher. And we'll just put in some stuff here. So this is graphite. This one in green is going to be diamond. All right, let's chain them together. If we chain them together, we're going to have to flip the diamond. Ooh, I shouldn't. Okay, there's graphite, there's diamond. If we chain them together, we're going to have to flip the diamond. We're going to go from graphite to CO2. You know what, let's actually write that in. Let's write, maybe in purple here. This is CO2. Ooh, CO2. And this is also CO2. Right, so we're going from graphite to CO2 and from diamond to CO2. We see that the graphite gets a little bit less energy released than the diamond. So let's flip the diamond and put it together. Let's make a two-step reaction. Let's graphically make a two-step reaction here. We're starting with what we want. We want to start with graphite. We want to go to diamond. So why don't we do this? We'll take our graphite, which starts here, comes up, comes down, goes to CO2. And then that CO2 right, can become diamond. So we basically, what we've done, if we've chained the two reactions, we've chained the two reactions through the CO2, the bottom here, and we have to flip the diamond. We have to flip this diamond reaction. And when we flip it, it reverses the sign. If it releases energy going one way, it has to take the same amount of energy going the other way. So what we end up with then, if we use some arrows here, this releases, that from there to here, we know that it releases a certain amount of energy. It releases 394 kilojoules minus 394 kilojoules. Going up from CO2 to diamond is the reverse of this reaction. We have to flip it. We have to flip it. And flipping it will reverse the sign. So this is plus 396 kilojoules. So we go down, we go up. And so then our answer is combined energy, right, is going to be minus 394 kilojoules plus 396 kilojoules, which is equal to plus 2 kilojoules, right? Plus 2 kilojoules per mole. So 1 mole of this reaction would take 2 kilojoules of energy, just 2 kilojoules. A very small actual change, just that lattice energy of the diamond, I guess. Yeah, so that's Hess's law. That's how we think about it. We see what kind of steps we can do, and we chain it. We notice that we chained it using our CO2. We have the CO2. The CO2 doesn't show up here, so you know it has to drop out somehow. One way to think about this is the graphite here. Oh, I guess I had it in red earlier. Let me change it to red. The graphite here in red is on this side of the equation. So that's fine. And it's also one graphite. And the diamond is on the opposite side, right? The diamond needs to be on that side of the arrow. So we know that we have to flip it. We have to flip it. We have to flip the reaction, so we have to flip the energy. So that's the kind of logic we're going to be getting into with these Hess's law problems. Yeah, let's go to the next one. I'm going to pause. All right, let's do a second one. This one looks more complicated. There's 3 reactions to play with now, and graphically it's going to be difficult to do, but logically we can do the same kind of trick we did back here, where we looked at our kind of targets and saw where they ended up in the actual reaction. So let's just do that. Let's do that in color. So this is our first target, C2H6. Do we see it in our reactions? Yes, we do. It's over here, C2H6 gas. So that's good. This reaction is okay. That reaction is fine. We don't see the C2H6 anywhere else. So we can start with that reaction. Next up in green, we have C2H4, C2H4 gas phase. When we look at it, this is after, and let's just kind of, right, it's after the arrow, and here's the arrow, right, it's after the arrow. Here it is on the wrong side. It's on the wrong side of the reaction on this side here. We're going to have to flip it. We have to flip this reaction. Ooh. Right, so this guy, we want to flip it. Want to flip that that energy term and flip that entire reaction. Right, we're going to have to flip this entire reaction. It's going to be 2CO2 plus 2H2O to C2H4 plus 3O2. And then the last one here is the H2. We have a single H2. We have one H2 here. Over on this side, we have 2 H2s. So we not only have to flip it, we also have to divide by 2. Divide by 2. Right, we have to flip it and divide by 2. So this one, this here, is going to have to flip and divide by 2. So that's what's being suggested logically, because there's no H2 anywhere else. So those are our 3 targets, and that's what we have to do to them. We divide by 2 to get just one H2. And hopefully, all of that is going to line up and give us the correct overall equation. So what I'm going to do is I'm going to pause and write out these equations flipped and multiplied and so on, and I'll show you that it all cancels out correctly. So I've written it all out now. So I took number 1 and I just left it alone. C2H6 plus 3.5O2, 2CO2 plus 3H2O. Number 2, we said we had to flip it, so we have to flip the whole reaction. We have to flip it, the 2CO2, right, 2CO2, 2H2O, that's going to be on the reactant side now. And on the products, we have our 1 C2H4 and our 3 O2s. So that's on the reactant side. And then the last one, we have to flip it and divide it by 2. So we flipped it, H2O, and we have to divide it by 2. So instead of 2 H2O, it's only 1 H2O. Then we just, on the other side, we'd have H2 and O2, but instead of 2 H2, it's 1 H2. Instead of O2, it's half of an O2, 0.5 O2. So let's prove that things cancel out. Right? Let's actually prove that these things cancel out. Let's start with O2. Right? O2. On the left side, we have 3.5 O2. 3.5 O2. And on the right side, we have nothing on this side. We have 3O2 over here. And then down here we have 0.5 O2. Right? So that actually balances out. That's fine. That's going to be nothing. 3.5 oxygens, make 3.5 oxygens. So take 3.5 oxygens, make 3.5 oxygens. That cancels out. Next up is the CO2, which doesn't show up in our initial reaction. The CO2. The CO2, on the left side, we have 2 CO2 here, right, and nothing else, no other CO2s around. On the right side, we have the 2 CO2s up here. We're making 2 CO2s. And so that also cancels out, so that's nothing. We start with 2 CO2s, we end up with 2 CO2s. So nothing's going to happen there. We did the O2, okay, H2O. Right, on the left side, there's 2 H2O here, and we have 1 H2O here. On the right side, we have 3 H2O on this one, and no other H2Os, right? Just that 3 H2O there. So that's fine too. And that's all of the extras, right? That's all the extras, CO2, H2O, O2. So that takes care of everything, and then we have our C2H6, so then our overall here is C2H6. We know that we took care of the O2, we know we took care of the CO2, we know we took care of the H2O, making C2H4 plus the single H2, which is exactly what our target was. That's what we wanted. So that's a Hess's law problem. We figured out exactly what we needed to, right? That's our target, and that's what we got down here. So, hooray! Right? We've canceled out all of our extras that don't show up in our equation, and we've got our overall equation. Now the last piece is to figure out what's going to happen with this energy. So our energy, right? Our energy is equal to equation 1 plus minus equation 2 plus minus equation 3 divided by 2. Right, because that's what we did. We did equation 1, we flipped equation 2, and we flipped equation 3 and divided it by 2. And we can look at our energies here. This is minus 1559 kilojoules, minus 1559 kilojoules. That's equation 1. Plus, minus, and then the minus 1411. Minus 1411. I recommend this method because often you get confused with flipping and stuff. So having this kind of very specific mathematical process is helpful. Minus, and then equation 3 is minus 572. So we put that in for 3. Minus 572 kilojoules divided by 2. And we'll throw that all through our calculator. Alright, that's minus 1559 kilojoules plus minus minus. So plus minus minus comes up to plus 1411 kilojoules. And then plus minus minus again is going to be again plus 572 divided by 2 is 200 and, you know what, too lazy. 572 divided by 2. 286, so plus 286 kilojoules, and then we get our answer, minus 159559 plus 1411 plus 286 is 138, so plus 138 kilojoules. So plus 138 kilojoules per mole is our energy, is our final energy. So that's how you do a Hess's law problem. You can use your target equation to get hints as to what to do to your givens, and you do them. You check to make sure everything's correct by canceling out your different byproducts. Another thing that I've seen people do is just, there's 3.502. Well, if I take the 302 here, right, I can take out the 3, and then the 0.5 will take out the 0.5 and stuff like that. There's 2 CO2 here that cancels the 2 CO2 here, and the 3 H2O, right, I would take away the 3 by getting rid of this 2, and then I could get rid of the H2O by getting rid of the H2O, and then I just have my C2H6, C2H4, and H2. So you have to make sure that that balances out. And then once you've got that, you use what you've said you're going to do to the equations to figure out what you're doing to the energies. So that's a standard Hess's law problem. We're going to do one more, so I'm going to pause and we'll set up for the next one. Okay, here's another practice problem. This is a nitric oxide one. This is our target equation here. 2NO plus O2 to 2NO2. And these are our givens. This is what we get. We have to figure it out. So let's try that same process. We have 2NO, 2 NOs. Well, here we have NO. Right, there it is. So it's on the right, it's on the correct side. It's on the correct side of the equation. But there's only one of them. There's 2 of these in our target. And I don't see any other nitrous oxide anywhere. I don't see any other nitrous oxide anywhere. So we are going to multiply this by 2 times 2 times 2. When we multiply it by 2, that also is going to take care of our NO2, right? Because there's 2 of them on the product side, and that's going to take care of that, right? That's going to take care of it times 2 as well. So that one's going to get multiplied by 2. Great. Problem is this oxygen, right? This oxygen that's going to have to get taken care of. We have oxygen, when we look at the oxygen, we have oxygen in 2 places. When we look at the oxygen, we have oxygen here, we have oxygen here. O2 gas, because this is ozone. We're also making some ozone on this side. So this gets a little bit more complicated. We also have oxygen here, actually. We have oxygen here. But let's look at this top equation, right? Oxygen, we have oxygen, we're making elemental oxygen, and here's the delta H. But that elemental oxygen, just O, doesn't show up anywhere else. There's no way we could possibly cancel it with anything, and it's not in our target equation. So this reaction is actually completely useless. It's a red herring. We didn't need that at all. We don't need that. We just need to play with these 2 reactions. This is what we can see when we talk about it. Oxygen then. We have to deal with this oxygen. In the top reaction, we might make oxygen by flipping it, but we've already decided what we want to do with this reaction. We want to multiply it by 2. That's the only way to get our 2 NOs and our 2 NO2s. So we can't touch this reaction anymore. We have to balance with this reaction down here. And we know at the very least that we're going to have to flip it. Right? At the very, very least, we are going to have to flip it. So let's try that. Let's just try flipping it and see what happens. And I'm going to do the same thing. I'm going to pause and write them out, and then we will work that out from there. And so I've written out the equation. Let's get a total down here. Well, we've got our 2NO and our 2NO2. Let's see what happens to these oxygens. 3O2 on, or 2O3 on this side, because I multiplied everything by 2, right? 2O3, so times 2. That and 2O3 on this side, those get to cancel each other out because they're on opposite sides of, the equal sign, I guess, the reaction arrow. 2O3 becomes 2O3. That cancels out. Over here we have 2O2. Over here we have 3O2. The 2O2 comes from multiplying this by 2. This 3O2 is just the flipped version of this reaction here, the 3O2. And so our 2O2 is going to go away, and this 3 becomes a 1, right? Because we're reducing it by, right, so 1O2. So our total then, when we actually write it all out, right, we're going to have our 2NO plus 1O2 because we have just O2, just O2, and it's going to make 2NO2 because the ozone, the O3, has been taken out. It's on equal sides. We start with 2 of it, we end with 2 of it, so there's no actual change. So there's our total, and hey, guess what? That's what we were targeting. 2NO plus O2 to 2NO2. And there it is, 2NO plus O2 to 2NO2. So that means that our times 2 for number 2 and our flip for number 3 is the appropriate way to do it. Hence, we are going to, hence we have the correct energy. So I'm going to write out the energy term. So I've got it written here. Energy is 2 times number 2, because we said number 2 times 2, minus number 3. So flip number 3. And 2 times number 2, flip number 3. So let's actually put those in. So 2 times number 2 is going to be 2 times minus 199. Oh, brackets, sorry, I wanted to have in brackets. Kilojoules plus minus, and then 3 is minus 427 kilojoules. Let's work our way through our brackets. 2 times minus 199 is minus 398 kilojoules. And then plus minus is just minus. So minus 427 kilojoules. Minus 427 kilojoules. Yeah. So that's that, and then we just put that through a calculator. So minus 398 minus plus minus minus. Sorry, plus minus minus is plus. What am I talking about? Plus minus minus is plus. So plus 427. Plus 427 is 29 kilojoules. Plus 29 kilojoules. So that's our answer. Per mole. We can figure out how much this reaction would take. It's plus 29 kilojoules per mole by using these other reactions. And in this case, we didn't need that first reaction at all. So that's some Hess's Law practice problems. I hope you enjoy them. We're going to do a bunch more in class. I really like these. They're like a little puzzle. So yeah, thanks a lot and see you in class.